Calculus Video 38, Derivatives of Inverse Trig Functions. So the derivative of an inverse trig functions, we should probably think about what's an inverse trig functions, which we'll get to in just a minute. But before we get there, it's easy to kind of look at this, okay, well, inverse trig functions, that's something that was maybe just a little bit important even back in trig. How important could their derivatives really be? Well, it turns out the derivatives of inverse trig functions end up being really important for us. All right, very important for Calc 2 and beyond. So even though this might seem like just sort of some kind of out there topic that's not very important, it is actually quite important for what we're going to be doing later on. So before we get to the derivatives of the inverse trig functions, let's just go back and remember what the graphs of the inverse trig functions are. Okay, so remember inverse functions, right? Inverse functions undo each other. So like if if we have like the sine of pi over 6 is a half, for example, then the inverse trig function, inverse sine, we would say the inverse sine of a half is pi over 6, right? It undoes the original sine function. The sine function, you're picturing it as a wave, right, kind of going along, the graph of which is a wave going along the x-axis. The inverse flips that, and now it's a wave going up the y-axis, except for that would not be a function because it would not pass the vertical line test. So what we do is we take that wave going up the y-axis, and we only use a portion of it that then creates a function. So if we're going to look at the graphs of the inverse trig functions, let's take a look at inverse sine of x, first of all. When you're doing the inverse functions, basically what's happening is the x and y axes are flipping from the original function. And so instead of going from -1 to 1 on the y-axis, we go from -1 to 1 on the x-axis. And on the y-axis, we have things like negative pi over 2, 0, pi over 2, pi. That's all we really need for this particular part. Okay, what you're picturing again is that sine function winding around the y-axis instead of the x-axis. If you remember, the sine function passes through the origin, so you still get the origin. And the sine of pi over 2 is 1. The sine of negative pi over 2 is -1, so therefore the inverse sine of 1 is pi over 2, the inverse sine of -1 is negative pi over 2, and it's not a straight line here though, right? It's the sine function, it's winding itself around here, right? I mean, that's a terrible graph. It would look something like this if you kept it going. It would look like this, and then this, and then this, right? And you'd have this whole sine function winding up along the y-axis, but we only have this portion of that. Again, that's not great. Let's try it this way. There we go. That's pretty good. We only have this portion of that sine function, the inverse sine function. That way it's a function. It passes the vertical line test. Only one y value for every x value. I said it's pretty good, then I didn't like it anymore. There we go. That'll work. All right, so that is what the inverse sine of x looks like. Notice the domain here goes -1 to 1. The range, negative pi over 2 to pi over 2. Okay. So we need to know that graph. We need to be able to picture that graph. What we're going to do is take the derivative of that. We're going to find in this video what is the derivative of the inverse sine of x. What function gives the slope of the tangent line at every point on the value of x there on that curve, right? So we're looking for, at any point x, what is the slope of the tangent line on the curve there? What function tells us that slope? That is the derivative. That's what we will be looking for. Okay, but let's continue on with just the functions, just the graphs of the inverse trig functions. Make sure we have all of those down. For inverse cosine of x, again, here's 0, here's negative pi over 2, here's pi over 2, and here's pi. Once again, from -1 to 1. Remember that for the original cosine, the cosine of 0 is 1. Therefore, when drawing this one, the cosine of 1 is 0. The cosine of pi over 2 is 1, the cosine of pi over 2 is 0, therefore the inverse cosine of 0 is pi over 2. The cosine of pi is -1, therefore the inverse cosine of -1 is pi. Again, not a straight line here. Again, you're picturing this cosine graph, right, winding up the y-axis, kind of, all the way through. And this one actually would kind of go back this direction, right? This is winding up. That's not a function because it would not pass the vertical line test, so we only use a portion of it. Unlike the sine graph, however, the portion that we're going to use for the inverse cosine is from 0 to pi. We can't use from -pi/2 to pi/2 because it would look something like this. It would be from here to here. And that also is not a function and does not cover the entire domain -1 to 1. So we go from 0 to pi on the range here, and it looks something kind of like that. Right, so that's the graph of inverse cosine. Once again, the domain is -1 to 1. But this time, the range goes from 0 to pi. All right, just some recollection of some things we should have learned in trigonometry. All right, inverse tangent of x. Well, picture the graph of tangent of x. If you remember that, tangent of x goes through the origin, and it has vertical asymptotes at pi over 2 and -pi/2 and 3pi/2. What's happening is the x and the y are flipping. And so now instead of vertical asymptotes at all the pi's over 2's, you're going to have horizontal asymptotes at, say, -pi/2, pi/2, 3pi/2, things like that. And you get a tangent graph that looks like this. Sorry, an inverse tangent graph that looks like this. Okay, the domain here is all real numbers. The range goes from -pi/2 to pi/2, but it's exclusive, as in it uses the parentheses, not the brackets, because the curve never actually reaches -pi/2 or pi/2. Like so. All right, so there's inverse sine, inverse cosine, inverse tangent. Let's do the reciprocal functions: inverse cosecant, inverse secant, and inverse cotangent. Inverse cosecant. I'll quickly draw, just to remind yourselves, what does cosecant looks like? Remember this, we start with a sine graph, and I'll erase all this here in a second. And then you do the vertical asymptotes, right? If you're looking for cosecant, right? Not inverse cosecant here, just cosecant. And then the cosecant graph, which is the inverse, sorry, going too fast. The cosecant graph, which is the reciprocal of sine, looks like this. All right, this is just the graph of cosecant, not inverse cosecant. Okay, now what we're going to do is we're going to take this graph, this curve in green, and we're going to flip the x's and y's. And so it's going to look something like, flipping that over, flipping the x's and y's, we get something like this for the inverse cosecant. There's 0, there's -pi/2, there's pi/2. There was a horizontal asymptote at y equals 0. Don't forget my 1 and -1 here. At 1, it will be pi/2, because cosecant of pi/2 is 1. And what happens is it goes from this point here towards that horizontal asymptote. And then at -1, you get -pi/2, and then it goes again towards that horizontal asymptote. This is kind of like, it's like half of, this curve that would have looked like this, but that would make it not a function, so we don't use the top or the bottom half down there, and we just get something like this. That is the graph of the inverse cosecant. A couple of things to point out. One, domain here. Domain goes from -infinity to -1, union 1 to infinity. Range, there's that horizontal asymptote at y equals 0, the dotted red line there, that the curve never actually touches. So this range is actually from -pi/2 to 0, union 0 to pi/2. And one other thing to point out, the slope of the tangent line, thinking about the derivative here upcoming. The slope of the tangent line, pick any point on the graph of inverse cosecant, and notice that that slope is always negative. The slope of the tangent line for the inverse cosecant is always negative. Therefore, the derivative will always be negative as well. Okay, let's do inverse secant. Running out of room here, so maybe I'll do this just to give myself a little bit more room. Hopefully I left myself enough room. Y equals inverse secant of x. Same idea. Negative pi over 2 there, pi over 2 there, pi here, 1 and negative 1. This time the horizontal asymptote is at pi over 2. And the curve looks like this. The inverse secant of 1 is 0. That's because the secant of 0 is 1. And it goes towards that horizontal asymptote. The inverse secant of negative 1 is pi. That's because the secant of pi is negative 1. And once again, it goes towards that horizontal asymptote like so. Okay, so the domain is negative infinity to negative 1, union 1 to infinity. And the range this time goes from 0 to pi, but not including pi over 2. 0 to pi over 2, parentheses, union pi over 2 to pi. Take a look at the slopes of the tangent line for the inverse secant. At any point you pick, if you look at the slopes of the tangent line, what do you notice about those slopes? Those slopes are always positive, whereas the slopes of the inverse cosecant are always negative. All right, and finally, one last recollection. I did not give myself enough room. Let's see. Why don't we just go back up here? All right, let's do y equals inverse cotangent of x. Much like the inverse tangent, 0, pi over 2, pi, negative pi over 2, where the inverse cotangent, the regular cotangent had vertical asymptotes at 0 and pi and 2 pi and negative pi. Therefore, we're going to get horizontal asymptotes at 0 and pi and negative 2 pi. And the curve then for the inverse cotangent looks like this. All right, going between two of those horizontal asymptotes, this time between 0 and pi. The domain for the inverse cotangent is all real numbers. The range goes between 0 and pi, but not including 0 or pi. Okay, you should know the graphs of your inverse trig functions. Okay. What we're going to do today is to look and try to find the derivative function of a few of those inverse trig functions. We'll start with the inverse sine of x. So what is the derivative of the inverse sine of x? What function gives the slope of the tangent line at any point on the curve of inverse sine of x? What function could that possibly be? Before we get there, there are 3 of these inverse functions that we'll use all the time. The other 3, quite a bit less. So the inverse sine of x, that's a big one. Put a big star by that one. The inverse tangent of x, put a big star by that one. And the inverse secant of x, put a star by that one. Those 3 derivatives end up coming up more often. We'll use those more often than we will the other 3. And the reason is the derivative of the inverse sine of x turns out to be the exact same thing as the derivative of the inverse cosine of x, only the inverse cosine of x is the negative form. The derivative of the inverse cosine of x is the negative of the derivative of the inverse sine of x. It's the same derivative, only the one for the inverse cosine has a negative sign with it. And if you look at that, think about this red curve here, the red line here, the slope of the tangent line I've drawn for inverse sine at x. If I drew that same position x here, what's going to happen is that slope, whatever that slope happened to be for the inverse sine, is the same as the slope for the inverse cosine. It's just that the one for the inverse cosine is negative. Okay, they're symmetric-ish, if you will. That's not even a real word, but they're kind of symmetric, where the slope of the tangent line is the same number. It's just the one for the inverse cosine happens to be negative. Okay, and that works for both inverse tangent and inverse cotangent, inverse cosecant and inverse secant. So if you will, I think I have this written down here. Again, we're looking for a function that gives the slope of the tangent line at each point on the curve. That's the derivative. That is the derivative. That's what we'll be looking for here in just a minute. And I said there's three of them that are really important. The inverse sine, that's really important. The inverse secant, that's really important. The inverse tangent, that's really important. Those derivatives of those three. And the reason we don't use the other three so much is because it's really the same derivative. You have the same slope for inverse sine as you do for inverse cosine. They're just opposite in sign. And so they end up with the same derivative, just opposite in sign. And the inverse cosine, inverse cosecant, inverse cotangent derivatives happen to be negative, whereas the inverse sine, inverse secant, inverse tangent derivatives happen to be positive, so we end up using the positive ones more often. Okay, so we're going to focus on those three. What is the derivative of inverse sine of x? What is the derivative of inverse secant of x? What is the derivative of inverse tangent of x? And we're going to walk through how to find each of those three derivatives. And then I'm going to come back at the end and say the derivative of inverse cosine of x is the same as the inverse derivative of inverse sine of x, but I'm going to throw a negative sign on there. And same with the inverse cosecant and inverse cotangent. And I know I've done this a few times already, but before we get there, we have to recall a little bit from trigonometry. And that's because we're going to prove the derivative of inverse sine of x here in just a minute. But we need this property from trigonometry. And you probably did this in trigonometry, but maybe you don't remember. So here goes. We have a composition of functions that we did in trig, where we have the cosine, in this case, of the inverse sine of x. Right? So we're composing two functions. We're composing the cosine of x as the outside function and the inverse sine of x as the inside function. The cosine of the inverse sine of x. A couple of things to think about here. Inverse sine of x. What we do for inverse trig functions is we put in values and it gives us out angles. For example, the inverse sine of 1/2 is pi over 6. The inverse sine of 1/2 is pi over 6. And the reason that is because the sine of pi over 6, because the sine of pi over 6 is 1/2. Right? The inverse trig function just undoes it. So what I'm saying is, for inverse trig functions, we put in values like 1/2 or √3/2 or 1/√2, right? We put in numbers, values. And we get out angles. The answer to the result of to the inverse trig functions are angles. We get out angles. So think about this in the cosine of the inverse sine of x. What we're going to do is we're going to plug in a value for x, and then we're going to take the inverse sine of it, and that's going to result in an angle. So the answer to this becomes an angle, which we'll call theta. And then we'll take the cosine of that angle, theta. Okay? So that's how you do that composition of functions. Only, we're not actually going to find out what that angle is. The actual angle theta we'll never find out. We'll just kind of use that idea that is some angle theta. So let's think about it like this. We're trying to find the cosine of the inverse sine of x. Let's say the inverse sine of x is equal to some angle theta, whatever that happens to be. Based on how trig functions work, in inverse trig functions, if the inverse sine of x is equal to theta, that must mean that the sine of theta is equal to x. Or, if you want to think about this, since sine is a trig function, and trig functions are defined as like parts of a side of a triangle over other parts of a side of a triangle. In particular, sine is the opposite over the hypotenuse. We often think of the answer to trig functions as fractions. So maybe we think of the sine of theta as x over 1. Okay. From that, we could draw a nice triangle. A right triangle, so we're dealing with trig functions right now. Let's call this angle theta here. And what we know is the sine of that angle theta is x over 1. Definition of sine is opposite over hypotenuse, so the opposite would be x and the hypotenuse would be 1. Well, what I want to know is, what is the side we have not named, the adjacent side? So just for a minute, I'm going to call it A. That way I can use it here, but I'm going to replace that with something in a minute. Because we have a right triangle, we can use Pythagorean theorem. Pythagorean theorem says that a squared plus x squared equals 1 squared. What I want to do is I want to solve for a. And so solving for a, I get a squared is equal to 1 squared is 1, minus x squared. And then I'll take the square root to solve for a. Therefore, a is equal to plus or minus the square root of 1 minus x squared. But this is just a distance. This is just some triangle I have out here. And so I'm going to use the positive here instead of plus or minus and just do a is equal to the square root of 1 minus x squared by the Pythagorean theorem. Okay, so I'm going to replace the a here, or just put equal to. A is equal to the square root of 1 minus x squared. Okay, very good. So we started again with this, whatever's on the inside here, this inverse sine of x. We said inverse sine of x is equal to some angle theta. Therefore, by trig functions and inverse trig functions, the sine of theta must equal x, or x over 1. We drew a nice triangle. Definition of sine, opposite over hypotenuse, x over 1. Pythagorean theorem to find out that adjacent side must be the square root of 1 minus x squared. Now let's go back here to our original. What I wanted to know was, what is the cosine of the inverse sine of x? That's the same thing as saying, since the inverse sine of x is theta, that's the same thing as saying, what is the cosine of theta? All right, just replacing inverse sine of x with theta. And by definition, the cosine of theta is the adjacent over the hypotenuse. Adjacent over the hypotenuse. The adjacent for theta is the square root of 1 minus x squared, and the hypotenuse is 1. Or you can just say the cosine of theta is the square root of 1 minus x squared. Or we could say the cosine of the inverse sine of x is the square root of 1 minus x squared. Done. All right, that's what we did back in trigonometry, and we may have done that thinking, where in the world could I possibly have used this? Well, we're about to right now. We are going to prove the derivative of inverse sine of x, but to do so, we're going to end up with this, what is the cosine of the inverse sine of x thing? And we're going to go through the same argument we just had, that the cosine of the inverse sine of x is the square root of 1 minus x squared, as we found with this particular problem from trigonometry. All right, so let's try it out. Let's give it a shot. So we want to know what is the derivative of the inverse sine of x. What is the derivative of the inverse sine of x? To do so, we're going to start with this. Let theta equal inverse sine of x, right? Because this inverse sine of x is equal to some angle theta. So, asking ourselves what is the derivative of inverse sine of x is the same question as saying what is the derivative of theta with respect to x. So for example, if I took the derivative of both sides here, d theta dx equals the derivative of inverse sine of x. All right. In other words, if I want to know what the derivative of inverse sine of x is, I just need to find out what is the derivative of theta. What is d theta dx? Those two things are now equal. The reason that's important is I'm going to rewrite this. I'm going to write this instead of theta equals sine of x. I'm going to write that as its normal sine function, not the inverse sine function. Instead of theta equals the inverse sine of x, the sine of theta is equal to x. And we're going to take the derivative from here. Okay. So, if I have the sine of theta is equal to x, I'll take the derivative of both sides. Derivative of both sides. And we're doing this implicitly with respect to x. With respect to x. And what I mean by with respect to x is we'll take the derivative of whatever variable we have, dx, right, with respect to x. So we'll have a dx on the bottom. Okay, so I have sine of theta equals x, the derivative of each one. So then we'll have the derivative of the sine of theta must equal the derivative of x, taking the derivative of both sides. What is the derivative of sine theta? Remembering to use the chain rule here because theta is a variable which is not x. The derivative of sine of x is, the derivative of sine theta is cosine theta times, chain rule says, times d theta dx is equal to the derivative of x with respect to x is just 1. All right, solving for d theta dx, we get d theta dx is equal to 1 over the cosine of theta. Okay, 1 over cosine theta, but go back to the top. What is theta? Theta is the inverse sine of x. And so the d theta dx is 1 over the cosine of theta, which is the inverse sine of x. And here it is, the whole reason we did that trig function thing just a minute ago. Let me write that a little better. The inverse sine of x. Is we want to know what is the cosine of the inverse sine of x. That's that whole triangle thing that we just did. Right? So we would, if you're going to redo it, the sine of theta is x over 1, triangle, theta, sine, x over hypotenuse 1. Pythagorean theorem, as we saw above, we get 1 minus x squared, the cosine of which is the adjacent over the hypotenuse. Right, so we get d theta dx is 1 over the cosine of the inverse sine of x, or the cosine of theta, which is the square root of 1 minus x squared over 1, otherwise known as the square root of 1 minus x squared. And there you have it. That's the answer. The derivative of theta with respect to x, which go back to the top, remember, theta is equal to the inverse sine of x. So the derivative of theta with respect to x is the same thing as saying the derivative of the inverse sine of x. Since the derivative of theta with respect to x is 1 over the square root of 1 minus x squared, we get that the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Done. We have found the function that gives us the slope of the tangent line at any point on the inverse sine of x. And I know it might seem kind of random, it might seem kind of out there, but we end up using this a whole bunch. One additional point. This part I find quite interesting is when we were doing the derivatives of trig functions, right, if we did like the derivative of, say, tangent of x, our answer ended up being other trig functions, secant squared of x, for example. But notice that when we took the derivative of the inverse trig function for sine, the derivative of inverse sine of x, the answer here is not a trig function. I find that quite interesting. We get this 1 over the square root of 1 minus x squared. Seems to come out of nowhere, but we get that when we kind of follow our nose with this particular proof. All right, so we're going to need to know that. Write that one down. You need to know that the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. This video is long enough, so we'll stop here. And on the next video, we will look at the derivative of the inverse tangent of x, and we'll look at the derivative of the inverse secant of x.